Hello, and welcome. If you're watching this video, that means you missed day 2 of our week 11 lecture for Foundations of Technology. Let's go ahead and get started. So we spent half the class finishing up the assignment from last time, which was assignment 19, and that's due Friday by midnight. The second half of the class, we spent exploring the next topic, which is going to be mechanical advantage and efficiency, and has assignment 20 to go along with it. Our objectives are to use the tools available to IntegrityCAD and to calculate mechanical advantage using relationships between force and distance, as well as to calculate mechanical efficiency. Let's go ahead and take a look at the second part. If you're having trouble with assignment 19, you should try emailing me or watching the previous video where I go over how to set up all the necessary constructions. So to start off with, we're going to talk about machines here. So we're going to explain how a machine how a machine makes work easier, describe some examples of force distance trade-offs. Nothing is free. We're going to describe and calculate mechanical advantage and efficiency as well. Lastly, we're going to take a look at why machines are not 100% efficient, and the answer to that is going to be friction. We'll take a look at that. So what is a machine? Machines make work easier in some fashion. Now, what that is could depend on the machine. It could be changing the amount of force you have to exert. It could be changing the distance over which you exert that force, or it could be changing the direction the force is exerted. What's easier, opening a can of paint with your fingers or using a screwdriver? Obviously, using a screwdriver is going to be simpler because you don't have to put as much force on it. It's a lot easier to do. This tool both multiplies and redirects the force. You push down, the force goes up on the other side. So, very interesting tool, very simple, but very effective. For lifting a box, a similar thing could be done using a ramp. If you lift straight up, you obviously have to use way more force than if you push the box up the ramp, but also pushing forward may be a little bit easier than lifting straight up. So you're redirecting as well. So we have two forces we're looking at. There's going to be an input force, which is the force you apply to the machine when you are doing the work. And we'll take a look at what work is in just a moment. And the output force. That's the force your machine applies on whatever thing you're trying to influence in its output of work. Now, what is work? Work is input force times input distance. Force over a distance gives you work. If I lift up my mouse, I'm doing work on it. I'm applying a force enough to overcome gravity for a distance, and that distance depends on how high I move it. So the farther, the more work, the more force it takes, the more work. So that is what work is. Output work is the same. How much output force you have times how much distance it went. So how do we relate these two types of work? Well, ideally, if there is no friction at all, the work you put in is exactly the same as the work you get out. So you might say, what's even the point of having machines then, if what you put in is what you put out? What gives? Well, the trick is in this equation. If we break down work into its components, force and distance, we are going to see that we can change one of these while changing a different one on the other side. So we can increase a force over here, which would, of course, be a way to increase the distance on the other side, or you could increase distance here and increase force on the other side. So by altering different variables on either side, you're going to create some kind of advantage for yourself. There's always going to be a trade-off. You cannot look at this equation and change just one side. That's not allowed, mathematically or physically. So what kind of trade-offs are we looking at here? Well, you can, for instance, decrease the force needed and increase the distance, or vice versa. You could increase the force needed and decrease the distance. We can take a look at a couple of examples. For instance, if you look at a wheelbarrow, Over here, the green arrow represents a small force being done over a greater distance, and the large force over on this other side applied over a shorter distance. So we can lift those really, really heavy rocks inside the wheelbarrow, despite not having to exert too much effort. We can look at the opposite over here with the hammer. So we have a large force being applied over a very short distance where we hit the nail, and a small force applied over a long distance where we go to move the hammer. Now, mechanical advantage is what you ultimately want out of a machine. It tells you how many times the machine that multiplies the force by. So a machine with a large mechanical advantage can lift a very heavy load much easier. We're going to be looking at actual mechanical advantage in this class, which you can find by taking the force you get out of a machine and dividing it by the force you put in. Now, this takes into account friction, because friction exists in the real world. You could also look at the ideal mechanical advantage by looking at distances instead. We're not going to do that in this class, but it is something that's done in physics, so I wanted to mention it. All right, let's try it. What is the mechanical advantage of a machine that applies 200 newtons to an object when you put 50 newtons of force in? Well, our equation is to take the force you got out and divide it by the force you put in. It's going to be 200 divided by 50, which gives us 4. Very, very straightforward machine. Pretty good mechanical advantage. Everybody's happy. Now, looking at something like this, you might get a little worried or confused. If you apply 2,000 newtons and you only get 200 out, well, that would mean we take 200 and divide it by 2,000, and our mechanical advantage is 0.1. Well, that's a horrible machine, you might say. For every pound of force I put in, I get 1/10 of a pound out? Horrible. What's the point of this machine? Well, there's going to be a distal advantage to this one. Think of your bicycle. If you go to a really, really, really low gear, it's really hard to pedal those pedals, but every little bit you move the pedal, the wheels move quite a bit. Same thing is happening here. We're either going really fast or really far using this machine because we have to work really hard, but something somewhere is moving really quickly because of that. Lastly, let's take a look at this machine. You put 10 newtons in, you get 10 newtons out. 10 divided by 10 is 1. Is there a point to this machine, you might say? There could be. This machine could be redirecting your power. So let's say I'm trying to pull on a rope. If I just pull straight up on that rope, that might be really difficult for me. I have to use a lot of muscles. If I redirect the rope through a pulley in my ceiling, I will not create any mechanical advantage for myself, but it'll be easier to pull. So this machine could still be useful if it's creating some kind of redirection of the way that the force needs to go. So takeaway, there is no mechanical advantage if the mechanical advantage is 1. If it's more than 1, the machine makes work easier in terms of the force you have to put in. If it's less than 1, it makes the work harder, but you're getting some kind of distance or speed as a result as a positive. Next, we're going to take a look at efficiency. So with efficiency, we have the following. Work in, work out, right? However, some output work is lost due to friction. Friction is one of those pesky things we can never fully get rid of in the real world. So we can figure out efficiency by looking at how much work we put in and gauging how much work we got out. No machine is ever 100% efficient. We are always losing something. What could we do to reduce friction? Well, you could lubricate something or make it out of a smoother substance. So let's see. We have a machine that takes in 40 joules and produces 30 joules. A joule of work is, again, remember work is force times distance. So a is the amount of work you get when you apply a force of 1 Newton over the distance of 1 meter. So in this case, we have 40 joules we're putting in, we get 30 joules out. What gives? Well, the amount we got out divided by the amount we put in times 100 will give us the percentage of efficiency for our machine. So in this case, 30 divided by 40 is 0.75. So this machine is 75% effective. And we'll lose about a quarter of our work due to friction. That would be pretty bad in the real world. Usually we want to strive for a little bit more efficiency than that. Looking at another example, let's say we have 250,000 worth of work that we are going to be putting in. The mower is going to give us 200,000 out. So this is an 80% efficient machine. Hopefully all of that makes sense. If it doesn't, please send me an email and I'd be delighted to work with you on an individual basis. Have a fantastic weekend. If you did not get a chance to pick up materials, don't forget that there is a hands-on project coming up, and you do need to have the following things to participate: 20 popsicle sticks, 4 rubber bands, and 2 paper clips, as well as some sticky tape. If you can acquire these items on your own, great, go for it. You'll need them by next Friday. If you want to pick them up from the school, the last time to do that was today, so you missed it. You can contact me and we can set up an alternate time for next week. Or I'll have an alternative assignment that doesn't involve materials also for those of you who are far away and can't get the materials. All right, thank you very much. Have a good one.